Okay, so topping at 8 and 18. Is acids and bases. And like other topics, the SL is mostly conceptual with a little bit of math, and the HL does predominantly most of the math application of the concept here. And so with SL, it's a lot of kind of knowing reactions and knowing definitions and things like that. And so what we'll start off with is the definition of acids and bases. And for SL, it is only Bronsted-Lowry. Okay. Lewis acid-base definitions and higher level, we'll address that in the higher level portion of this. So an acid is defined as an H plus donor. Proton donor is also an acceptable definition because H plus without its electron is really just a proton. Whereas a base is an H plus or a proton acceptor. And while this is not the most all-encompassing definition for acids and bases, which is Lewis acids and bases, by the way, it's the best one for common applications because one, it's easy to see and identify just by looking at the reaction when something's acting as an acid or a base. And two, most of the most common acids and bases kind of follow this definition sufficiently for us to work with titrations and neutralization reactions. And so for our purposes, this is covers about 90% of the acids and bases and is appropriate for this level of chemistry. So we also have to know that if something is amphiprotic, okay, can act as an acid or a base, according to Bronsted-Lowry. So for it to be amphiprotic, it has to be able to donate or accept a hydrogen. And again, hence the term amphiprotic, not to be confused with amphoteric, okay? Amphoteric means that it can act as an acid or base, but for any definition, whether it's Lewis or Bronsted-Lowry. Amphiprotic is very deliberately used for Bronsted-Lowry because you have to have a proton to donate or accept. So be careful about that. When you write out a reaction for this, an acid-base reaction, something like okay, you'll notice the transfer of H pluses in the reactants here, okay? And also technically there's a transfer in H plus in the products in the reverse reaction as well. So you do want to keep that in mind. But if we're identifying here, this is our acid because it's donating its H plus to water. And therefore water is our base. But if you look on the other side, the same idea happens. But in this case, your H3O plus is your acid, and your F minus is your base. Now, if you're reading left to right, they're called considered conjugate acids and conjugate base. If you're reading right to left, then HF and H2O are your conjugate acid and conjugate base, respectively. So don't assume the word conjugate always means right. Like it doesn't always mean the right side of the reaction. So what they say is the IB defines as a pair of species differing by only a single proton. So a pair of species differing by only a single proton is considered a conjugate acid base pair. Now, you do have to be careful when you call it a conjugate acid base pair, because if they ask you what the conjugate base of something is, that means the result. So, like if I ask you, what's the conjugate base of HCl? Okay, what would the conjugate base of HCl be? Yeah, Zara. Differs by an H plus. So when you, yeah, Cl minus. Yeah, no, it's okay. So conjugate base is Cl minus here, because when you say conjugate base, you mean the species that now acts as a base, meaning the HCl acts as an acid. So the resulting base of the acid reacting. So make sure you think about that when you're kind of looking at these ideas. And every acid-base reaction, well, I shouldn't say that. Every acid-base reaction with water has two conjugate acid-base pairs. There's always the H, like the acid or base with its conjugate, and then there's water with its conjugate. And in this case, water is acting as the base, so H0 plus is its conjugate acid. So if you see water here, it can go in either direction. It can accept and form H0 plus, or it can lose and form OH minus. And that's the very definition of an amphiprotic species. Other amphiprotic species tend to be like polyatomics that are polyprotic. Polyprotic meaning having more than one hydrogen that it can give. And so, for example, HSO4 minus is resulting when H2SO4 loses a hydrogen. And it can either go to SO4 2 minus, or it can go to H2SO4. So polyprotic meaning more than one proton to donate, or more than one H plus. And so HSO4 minus is a result of one of those polyprotic acids. Monoprotic means one proton, diprotic means two. Just kind of remember that terminology here. So these are considered amphiprotic species. Actually, let me make clear that H2O and HSO4 minus are the amphiprotic species here. I don't want to make it sound like all of these are amphiprotic. It's not. It's just H2O and HSO4 minus. Questions about that? Up there. Now, actually, strength is a separate topic. Okay. So the next section of SL has to do with the properties of acids and bases. Okay. So these are the general kind of characteristics of acid bases. We're not talking about strength yet. We're not talking about how much it dissociates. We're talking about just how do general acids behave and how do bases behave. Okay. Acids tend to have more reactions that we can quantify and that we can measure. Okay. And so there's several reactions that you have to know of how acids behave with certain species. The first one is acid with reactive metal. Reactive metal being like group 1 or group 2 metals, like magnesium. Okay. And when you do that, you will make the salt and hydrogen gas. Now make sure your salt formula is balanced, because you have to remember that Mg is 2+, so therefore it is MgCl2. Don't write MgCl just because that's how many Cls you have on the left. You will have to balance this to make it work out in the end, but you have to write appropriate formulas for your products. So the salt has to be neutral. So Mg is 2+, Cl's -1, hence MgCl2. Two. Okay. Acid with metal oxide. Okay. A metal oxide, much like a metal hydroxide, is just a base. So when you have that, you form a salt and water. No hydrogen gas right now because of the additional oxygen in the metal oxide allows water to be produced. Notice in the first reaction, we had no oxygen attached, and so therefore there's no way to produce water. So you end up producing hydrogen gas. Oh, let me balance that there too. Acid with metal hydroxide, again, kind of repetitive, but if you have something like this, you're going to form a salt and water. So being able to predict those reactions, well, there's two more reactions actually, but knowing how to predict all these reactions is something that you would be expected to do, maybe on a multiple choice, like what are the products of this reaction, or on the short answer where you'd write the reaction for you to do stoichiometry later on and such. Okay. Now, acid with hydrogen carbonates and carbonates. Hydrogen carbonates are your HCO3 minuses. That's one of the 10 polyatomics that you have to know for the IB. And carbonate is also another one. So knowing your CO3 2 minuses and knowing your HCO3 minuses. Oops. When an acid reacts with a hydrogen carbonate or a carbonate, it still undergoes a double displacement reaction where you form a salt but the other product is H2CO3. And the thing with H2CO3 is it generally breaks up into these two, water and a gas of CO2. And the IB will take off if you write H2CO3 as a product, because you should be expecting to see bubbles in a gas when this reaction occurs. Just think baking soda and vinegar, right? There's this release of gas. That's all that is. It's an acid, acetic acid, or ethanoic acid, excuse me, with sodium bicarbonate or sodium hydrogen carbonate. And that reaction creates CO2 gas, and that's what causes that volcanic eruption that is most kind of commonly seen. It doesn't matter if it's carbonate as well, okay? It's still going to generate these two products. Now the ratio is a little bit different, but it's still going to generate these two products. Hold on a second. Yeah. And so a couple of things about this, being able to observe what's happening in a reaction here. Notice that in reactions 1 and 4, a gas is being produced. So that's how you tell that that's happening. With metal oxides and hydroxides, it's an exothermic reaction. So you're producing heat when these reactions occur. So that's how you know a chemical reaction is occurring, okay? You have to be able to observe a chemical reaction occurring. And so whether it's production of gas in reactions 1 and 4 or a heat released when reactions 2 or 3 happen, those are indicators of when a chemical reaction occurs. Questions about that? Now, a salt is essentially any ionic compound. Okay. I guess that originates, for our purposes, originates from an acid and a base. So you will be expected to identify what acid and what base would react together to form that salt. Okay. And so when you see something like NaNO3 as a salt, you have to imagine that the components came from an acid and a base. Okay. So what acid and what base would you most commonly guess here for this this salt? What would you guess? Yeah, Zara. HNO3. NaOH, exactly. You could always safely assume the hydroxide. And again, what you'll realize is that the salt comes in two forms of ions. And the first ion is always coming from the base. And the second ion is always coming from the acid. Okay, the conjugate base is going to be more negative. The conjugate acid will always be more positive. That's why they pair together like that. So you want to be able to look at a salt and go, okay, this is where it came from. The leftmost ion came from a base. The rightmost ion came from an acid. Just add the H2O back to both species, and that's how it works. And that leads us into titration, okay? And so titration is, again, a technique used to determine the concentration of an unknown solution, I guess here through neutralization. Because you can do titration in topic 9 and 19 with redox as well, and it's a little bit different. But in this case, we're dealing with neutralization. And with a titration, you have to be familiar with indicators. Essentially, an indicator is a weak acid that changes color based on pH. And so you use indicators to try to determine the equivalence point of the reaction. So you want to pair up an indicator that's pH change, color change is most closely related to the reaction that you're dealing with. I'm trying to be careful because I don't want to stray into the higher level topic too much right now because we will see that a little bit later. Yeah, I don't want to go too far there. Okay. And so this is kind of where one of their stoichiometry kind of comes into play, because when you have a titration, here, you have to understand that your moles of acid have to equal your moles of base in the correct ratio. Okay, I guess maybe I shouldn't write equal, I should say proportional to. Because if it's a 1-to-2 ratio, then the moles of base should be twice as much as the moles of acid. And that kind of revisits the idea of molarity being moles over volume. Okay, so you're going to be given a volume, a molarity, and you'll be given a known volume and known molarity, and then an unknown volume, and you'll have to figure out the molarity. So you'll be able to solve for one of these two species here, and that will allow you to solve for the moles of the other species, which then you can plug into here to solve for the molarity. Now, just remember that when I say something has a 3.5 moles per decimeter cubed, the way you expand that out is 3.5 moles over 1 decimeter cubed. That's how you expand that unit. So that way, if you're doing factor label, or you're doing proportion method, this is how you expand that to serve the purpose of your calculations here. So if you have a volume of an unknown solution, you can set it equal to that to figure out what moles you have in that solution based on the volume you have. So that's your conversion factor for the stoichiometry here. Questions about that? That's one of the two, I guess, calculations you would actually be asked to do in SL here. HL, you would have to be expected to interpret titration curves and read like the volume off the titration curve and find the equivalence point, things like that. But for SL, it'll be a fairly straightforward kind of word problem where they provide you information, they ask you to solve for it. They'll probably ask you to write the reaction, balance it, and then given the volume and molarities, solve for the unknown molarity. And so you'll be given all the information in the problem, you just need to apply it. Whereas HL is going to have to kind of more extract the information from different resources. Questions on any of that? Okay. I'm going to skip around here because I think it makes more sense to do this part first. Okay. Strong and weak acids and bases. And just for the record, what I'm doing here is I am using the IB syllabus tracker that I provided for y'all on the Schoology website to kind of get over all these bullet points. I'm trying to hit all the major bullet points in this topic. And so if you go back and watch this video later, I should be hitting most of the bullet points that are in this topic because I want to make sure, because this is what the IB has said that you're expected to know. So I'm going to try to take it to the letter of the law when we're revising here and try to hit every single detail in this. Now, we may not be able to do examples of everything, but at least cover the content and hopefully you can apply it. So if you want to print out, like that's something I feel like you may want to consider doing, is printing out the syllabus tracker, kind of keep track of which statements you feel comfortable with and which ones you don't feel comfortable with, and help you review that, because there are a lot of details in there that will kind of get you if you aren't completely comfortable with the subtopic or the topic. And so really kind of go through there and look at those statements, go, do I know this or do I not understand this? And that will kind of help you focus on what you want to revise as well. Okay. And be honest with yourself, right? Okay. Strength in our terms with this topic is the amount of dissociation. How much is it dissociating into ions? Which is a little bit redundant, but I just want to kind of keep that in mind. Okay. And so strong considers 100% dissociation or ionization. I guess ionization in this case is a more appropriate word. Dissociation is more of an all-encapsulating word. Ionization is kind of more of an appropriate word here for this. Whereas a weak dissociates or ionizes partially, usually something like less than 1%. So there's a big gap. There's not many acids or bases that are considered strong that fall in that gap, or weak that even fall in that gap. It's usually all 100% or less than 1%. I think maybe HSO4 minus is like 50%, but there aren't that many that fall in between that gray area. Now, relating a strong versus weak, okay? And we talked about this in the topic, but being able to differentiate between an unknown strong and an unknown weak species is important. And there are multiple ways that you can do it experimentally. The first way is conductivity, because that measures ions in solution. So if you have a strong species, whether it's an acid or a base, it will have a high conductivity. And if it's weak, it will have a low conductivity. It will have some conductivity. It'll just be very, very low. And this is also something I want to key in on. And when you're answering this type of question on the IB, whenever you're comparing two things, you have to address what you would expect to see in both species to get full credit. You can't just say, oh, the strong acid would have high conductivity, because that doesn't explain that you understand that the other one has low, right? Because maybe they both have high. And the IB grader can't interpret what you're saying as an assumption there. They're not trained to kind of assume that you're implying that. And so when you say a strong acid would have high conductivity, you have to say a weak acid would have low conductivity, because that's how you prove that you understand the contrast between the two. So make sure you address both species whenever you're comparing, okay? That applies in acid base, that applies with reaction rate, that applies with molecule shapes, that applies with periodic trends, that applies with everything. If you're comparing or contrasting, or comparing and contrasting two species, you have to address for both species to get full credit. And I don't think the IB, even if you write all of the right answers for one of the species and you don't address the other one, you won't get credit. So it's not a, oh, but I got half of this right. That's the wrong half. You can only get half credit if you get half of both species right. So like, yeah, so like, let's say this question was like, how would you like name one experimental technique to differentiate between a strong acid and a weak acid? And you would say measure conductivity. Okay, 1 mark. If you just say a strong acid would have high conductivity, you wouldn't get a mark. Like the mark requires both of you saying strong acid would have high conductivity and a weak acid would have low conductivity. That's the 1 mark. Both of those statements have to be stated for you to get it. So don't lose a mark on questions like that. Two. Let me, you know what, let me write. Reaction rate. And this only deals with acid reactions. So this only really helps you if you have a strong acid or weak acid. But a strong acid should have a high reaction rate. You would call it a vigorous reaction. Because the ions are already dissociated, they are readily available to react with the metal immediately. Oops. Whereas weak would have a, actually we'll say low or slow reaction rate. Having said that, if I have the same molarity and same volume of a strong acid and a weak acid, how do I expect my amounts of products to compare if that's the limiting reactant? How do I expect the amounts of products to compare if I have the same molarity and the same volume of a weak acid versus a strong acid? How do I expect them to compare? Yeah, Zara. Yeah, the product. So if I put in the same amount of weak acid, the same amount of strong acid, and I put excess metal in there, okay, and it reacted, okay, when the reactions are over, how would the amount of gas in both those reactions compare? Well, okay, so here's the key, you gotta be careful of that, because what determines how much gas is produced? The number of moles. And if you have the same volume and the same concentration, you have the same number of moles. Yeah, so they're actually going to be what? The same, exactly. So now the rate is faster. You will produce H2. Like if you don't let it reach completion, you are right. The strong acid will produce more gas. But if you wait till all of it's reacted, whatever time that takes, it should produce the same amount of gas. And that's what, yeah. Yeah, eventually they plateau at the same point, exactly. And so the same amount of product produced if same moles. Okay. And that's the thing that I think sometimes students like kind of get conflicted with, because they're like, well, you produce it faster, so you're going to produce more. It's like, no, you're going to produce more per second, but you will overall still produce the same amount because you have the same amount of acid. It will just take longer with a weak acid. And so that's a common multiple choice question. They'll be like, a weak acid and a strong acid of same concentration, same volume react with magnesium metal in excess. State the following values that would be the same and which ones would be different, right? And like you have to go, okay, the volume of gas produced would be the same. The reaction rate would be different. The moles of both acids would be the same. Things like that. That's kind of a thought question that they would apply for that. Now, another way you can measure it is technically pH or a titration. That's all kind of grouped in the pH stuff. Generally speaking, the question will say, other than pH, how would you measure it? So I don't even like really take pH very seriously as an option because it's generally not allowed to be an answer. But yes, if you have a strong acid and a weak acid of the same concentration, the pHs will be different. The strong acid will have a lower pH. Let me write that down. A strong acid will have a lower pH, and a weak acid will have a higher pH. And the caveat is if it's the same concentration. That's a caveat, because there are technically times where I could make a weak acid have a lower pH than a strong acid. If I dilute the strong acid enough, I could very well have an acid, a weak acid that has a lower pH than a strong acid. So the key thing here is that they have the same concentration. That way you can compare things. You'll find actually throughout all of chemistry that anytime you're trying to compare stuff, there's always something that's the same about it, and there's always something that's different. And the sameness of the characteristics allow you to identify the one difference. You know, it's just like in your IAs. When you do an IA, when you come up with the experiment, everything needs to be the same except for that one factor. And that way, when you get results, you know it's because of that one factor. Just like in this idea, you know the pH is lower because of the dissociation or the ionization, because you've kept everything else the same. Temperature, the amount of the concentration, and all that stuff in there. Now, the volume doesn't really matter because pH just measures concentration, but you've eliminated all those other variables and are able to compare them. And conversely, with a strong base and a weak base, a strong base would have a higher pH. Oh, I do want to go back to one thing that I didn't talk about in reaction rate. Remember, you can measure reaction rate a lot of different ways. You can measure the amount of gas being produced. You can measure the amount of mass being lost. But you can also actually measure neutralization reactions based on what? What could you measure about a neutralization reaction of about an acid with a base? What aspect of it could you measure that would allow you to tell you how fast the reaction is occurring? We talked about it a little bit earlier. Yeah. Well, wait, say it again. Well, okay, so let me phrase this, okay? What do we, so whenever you measure a rate, you're really measuring a product or something that's being produced, right? It could be a gas. In neutralization reactions, what do you produce when you react an acid with a base? Salt and also one more additional thing that you can measure. And we just talked about it's what we talked about very quickly is that it produces heat. So you could actually measure the temperature change of the reaction to see how quickly, how fast it got hotter. and that would tell you how quickly the reaction rate happened as well. I think that was actually on one of the short answers a few years ago. They gave you a neutralization reaction and asked you to determine the rate, and you'd actually have to look at the temperature change because the strong acid would neutralize more quickly than the weak acid. Questions about any of that? Okay. Let's talk general examples of strong acids and strong bases and weak acids and weak bases. Okay. Your strong acids. Okay. Are only three for the IB. Okay, they are HCl, HNO3, and H2SO4. One second. Okay. So now in university, they might add additional acids in here. They might add HBr, HI, and HClO4 later on, because technically they are strong acids, but the IB, in an effort to minimize what you have to memorize, said they don't behave any differently. So why are we making you memorize 6 when you can only need to memorize 3? So the IB says, just know these 3, these are the most common ones. They achieve all the purposes that we want to do with acids and bases. So just know these 3. So know these for the IB. Your weak acids are all the other ones. So if they don't fall into the category of those 3, they are considered weak. So the most common ones we have are like ethanoic acid, CH3COOH, hydrofluoric acid. And that's a tricky one because unlike the other strong acids that are all the the halides, this is the one that's weak. And so HF shows up a lot. HCN, cyanic acid, is another common one. Maybe even H2CO3 as well. But all of these kind of accomplish the same thing. The only thing you have to really be careful about is with organic acids, the H is at the end. So because it's part of that carboxyl group. And so just know that it's written that way because that's the structural formula. So you have to be able to identify that quickly. Your strong bases. Okay, are essentially your group 1 and 2 hydroxides and oxides. Okay, so group 1 and group 2, alkaline metals, alkaline earth metals, those plus hydroxide or oxide form the group of strong bases. Every other hydroxide, like transition metal hydroxides, they are considered weak bases. They don't dissociate 100%. And so weak bases, all other bases. Now, that means all of the hydroxides, all of the oxides, but then also a couple of different amine ones as well, you know, NH3, Ammonia is a common one. CH3NH2 is another one. Aminomethane or methanamine. Transition metal hydroxides, things like that. Group 3 or 13, I should say, oxides like aluminum oxide, things like that. Those are weak bases. Actually, yeah, aluminum oxide is kind of amphoteric, but that's okay. So be able to categorize all these because you should be able to identify characteristics about them and how they would behave and how you differentiate between them. Okay. Questions? The pH scale. Okay. The pH scale is an artificial scale used to represent the hydronium concentration or H plus concentration in a solution. Okay. It's artificial in the fact that we take the actual values and manipulate them to make it a more relevant scale that's easier to comprehend and easier to understand. And so it's not that like it's completely made up. It is still based on empirical data. It's just presented in a different way. And that's the idea that negative log equals P, because these concentrations are so small. If we're looking at actual scale of H, it'd be from like 1 times 10 negative 1 to 1 times 10 negative 14. And that doesn't make a lot of sense. It's kind of hard to visualize that. And so they created the pH scale to make the numbers more accessible and easier to kind of identify. And so therefore pH is equal to negative log of H plus or negative log of H3O plus. And vice versa, the H plus concentration is equal to 10 to the negative pH. If you rearrange it, bring the negative over, then 10 to the x both sides, you'll get that as well. Now, this is given to you in your data booklet. This is not. So trust your algebra skills and be able to manipulate that equation as necessary. I wouldn't worry about too much memorizing that though. Because this is a logarithmic scale, one pH unit represents what factor of concentration change in this scale. What factor? Yeah, so, but if I said, for example, Zara, if I said 4 to 5, like pH of 4 to 5, what's the concentration difference between a pH of 4 and pH of 5? What factor is it? Wait, say it again. It's just 10, right? So it's 10 times the concentration change. Now, from 4 to 5, it's 1/10, because when you're increasing pH, you're decreasing concentration. Because remember, it's negative log, so it's kind of backwards, right? So like, if the number's getting bigger in pH, that means it's getting less H plus, because the value up here makes it smaller and smaller, right? So if you're saying pH of 4 to 5, the pH of 5 solution has 1/10 of the concentration of the 4. Or you could say the 4 has 10 times the concentration of 5. If you said 5 to 7, then the 7 is 100th of that. And it's 10 times 10 for each pH unit. The smaller number, yeah, because it's negative log. That negative is what throws off kind of the wrench and everything. Oh, okay. So you should know that for SL, that if I give you a pH and I give you a different pH, you should know the number, the factor at which it changes. Every unit of pH is 10, a factor of 10. So, I mean, I guess you could do like 10 to the negative delta pH, I guess. So like, would it be negative or would it be just positive? I'm trying to think of the best way to do this. Negative, because if you do the final minus initial, then it's negative, right? Yeah. So if you do final minus initial, so like 7 minus 5 is 2. So then 10 to negative 2 is 1 over 100. Actually, I don't like that equation, so I don't want to confuse y'all. So let's just keep it simple and just go factor of 10 every unit of pH. Okay. Now, okay. For SL, Kw is equal to H plus times OH minus, which is equal to 1 times 10 to the negative 14, which is Kw at 25 degrees Celsius. Now with HL, that value can change, but for SL, it will always stay that way, which means that neutral for SL is always going to be H plus is equal to 1 times 10 to the negative 7, which then makes a pH of 7. Okay. Because neutral, again, means when OH minus and H plus are the same. That's the definition of neutral, not pH of 7. It's when the concentrations of H plus and OH minus are the same. So keep that in mind with neutral. Okay. So you have to be able to manipulate values back and forth between pH and pOH. And again, for this, pH plus pOH is equal to pKw. And in SL, that'll always be equal to 14. So that's another kind of concept that you can kind of maintain with that as well. Understanding how to use a pH meter and an indicator, universal indicator. pH meter is just really a probe that measures, in actuality, measures the conductivity of the solution, and like that's how it tells how much H plus is in there. That's why it's not really accurate around neutral, because it's hard to differentiate between the difference in H plus and OH minus concentrations. And so, like, if you put a pH probe in distilled water, you won't get 7. Like, it's not calibrated that way. It's meant to kind of measure the differences between relative to water. And so you may get 6 for your distilled water pH just because it's really inaccurate around that point. A universal indicator is essentially a mixture of indicators used to qualitatively identify the pH. So it's not super accurate, but It's like 5 different indicators mixed together such that the color changes like the rainbow from acid to base. So as strong, like, sorry, I don't want to say strong acid. A low pH and a very acidic solution has a red color. Neutral is kind of green, and then very basic is blue/violet. So it kind of goes with the rainbow. Here. So just know that that's kind of the way that works. Questions on that so far? Last subtopic, and this is a subtopic, again, that's new for this cycle of curriculum, and so it's one of those environmental impact ideas that the IB is trying to reinforce in this new curriculum. So this ozone layer, like maybe not renewable energy and stuff like that, but other kind of pollution and stuff like that is something that they're going to try to address, especially in the short answer. They'll find a way to make a 2-mark question out of it. And so what you're dealing with here is acid deposition, which is all forms of precipitation, not just rain, right? It can still be the reaction of the chemicals with running water or in other types of precipitation, snow, stuff like that. All of that is still related to the reaction of these oxides with water to form that. Okay. So what you need to remember is this, okay? Rainwater is already slightly acidic, pH of 5.6, because of CO2 in the atmosphere reacting with water to carbonate it to make a slight amount of carbonic acid. So with acid deposition, it's where it's less than 5.6. So when the pH starts to drop, you will see it being considered acid deposition here. And so when it starts to drop, that means other oxides are reacting with water to form stronger acids and more dissociation of H+ ions. And so what you see are things like NO2 and SO2 and SO3 reacting, okay? And you need to know these reactions. Now, I say know the NO2 one really well because it's not one you could just figure out. The sulfur oxide ones are pretty obvious because you just combine them all, you just mash them all together. The NO2 one is tricky because you form 2 different nitrogen-based acids. You form nitric acid, HNO3, and HNO2, nitrous acid. So I say know that one because that one you might not be able to figure out kind of on the fly. The other ones, they just become that exact acid of them combined together. So with the sulfur oxides, they form the same sulfur-based acid as that, and the oxidation number stays the same. And so know these kind of reactions along with other period 3 oxides in topic 3. This is ones that you need to know. Okay, yes. Oh, they might ask you, write the balanced equation of how NO2 contributes to acid rain. So that would be, I guess that's as close as it being saying as write the whole reaction without giving you too much information, right? So I've seen that first reaction show up because that's the harder one to remember. Like, again, the IB wants to test to make sure that people don't stumble across the right answers. And so they usually ask about the NO2 one, not the SO3 and SO2 one. Okay. Now, sources of nitrogen, okay, sources of NO2, okay, there are naturally occurring and then there are synthetic, okay. Naturally occurring is, let's see, decomposition of plant matter. So part of the nitrogen cycle involves the decomposition of plant matter releasing NO2 into the atmosphere. So that's natural. The man-made is the internal combustion engine. Because the internal combustion engine takes normal air. It doesn't take anything different. It just takes normal air and combusts it, which is 20% oxygen, but it's also 74% nitrogen. So there is a case to be made that the nitrogen does end up combusting and produce some NO2 gas as part of the byproducts. Your SO2, actually, no, I should make it blue because that's what we're doing. Your SO2 and SO3 naturally is your volcanic eruptions. Okay. Volcanic eruptions, when they occur, do release a lot of sulfur. But anyone that tells you that the sulfur pollution problem is due to volcanic eruptions is grossly misquoting the actual values here. Like, yes, a volcanic eruption per like unit time releases more sulfur into the atmosphere, but total quantity wise, it's really more attributed to the man-made, which is burning of coal. Okay. So when you burn coal, there is sulfur that's embedded in the coal, and that gets burned as well, and that forms the SO2 and the SO3. Questions about this? We're almost done. We're kind of hitting the home stretch. Okay. Maybe like 2 more bullet points. Okay. Removal of SO2 and SO3 from that coal, or the sulfur from the coal, is a way that we try to mitigate our amount of sulfur dioxide being produced into the atmosphere. And so you can do pre-combustion, where you just remove the sulfur from the coal. Okay. That's a little more time tedious. That's a little bit more inefficient, but that is one way you can do it. And we won't go into the details about that. Post-combustion, okay, is where you react. It's chemical scrubbers. So what you do is you spray the exhaust gas of burning coal with a chemical which binds to the SO2 and the SO3. And so that is usually calcium oxide, which reacts with SO2 to make CaSO3. And that precipitates down, and they're able to remove the SO2 from the reaction there. Yes, sir. With the CaO. So an aqueous solution of this. which then binds to the SO2 and SO2, well, mostly SO2, because that's usually what's happening there. And that forms a calcium sulfite, which is removed from the flue gas. That's what they call the exhaust gas from burning coal and stuff like that. So that's why we call it a chemical scrubber, because you're spraying it with a chemical and it's scrubbing the CO2 from the exhaust gas. Very last thing for SL. Okay. Again, knowing some acid reactions with various things. So a couple of y'all did this for your IAs where you reacted an acid with a carbonate, right? So calcium carbonate is also considered limestone, and you end up forming that carbon dioxide. It disintegrates, slowly corrodes the calcium carbonate and breaks it down. Chemical erosion, right? Chemical weathering, I think I should say. Okay. But also, you can have those things react with metal as well. And you can form H2 gas. And so it will corrode metal as well. And so it says you have to know the acid deposition with reactive metals and carbonates. And so understanding how it reacts with those species to explain why the danger of them on external and outdoor statues and monuments and things like that is because those things are usually made out of limestone or metal and things like that. And after long periods of time, the small amounts of acid rain accumulating on them, they slowly react and break down. Questions? That's the end of the SL section. I'm going to take about a 10-minute break. Actually, you know what? 15, because I have to deal with something with robotics. So we'll pause the video right now, and then at 10:30, we'll resume again. So take a 15-minute break. SL, goodbye. Thank you for your attention. And I will see y'all in 15. Okay. This is the higher level aspect of the acid base section. So this is topic 8 and 18 here. I mean, sorry, 18, excuse me. So we're going to do a lot more calculations, and there's going to be rice charts and interpreting graphs and calculations, things like that. Nothing too significant. It's a lot of overlap with equilibrium calculations with rice charts and such, but still the application in acid bases is still important. And so, but first, we're going to do kind of the conceptual part of this, which is the Lewis acid base definition. Okay. So topic 18. Okay. The Lewis definition of acids and bases is one that is more inclusive. It's the all-encompassing one. It's the official definition that includes every single species that can be considered an acid or base, because there's no restriction of having a proton like Bronsted-Lowry has in its definition. And so a Lewis acid is known as a lone pair acceptor. Okay. And a Lewis base is known as a lone pair donor. Okay. Now, that seems to sound contradictory to what Bronsted-Lowry is, but you're thinking about it in terms of different perspectives. Whereas in Bronsted-Lowry, you were tracking the species that was moving. In Lewis, you're tracking the species and how they behave individually. And so what you have to think about is a base is accepting a hydrogen, which means it's forming a bond, which means that it has to donate electrons to form that bond. Hence why that aligns with this. So It's in terms of electrons versus protons, and therefore that's why the donor and acceptor part of it is opposite. Like if you think about, like, because all Bronsted-Lowry acids and bases are Lewis acid bases, but not all Lewis acid bases are Bronsted-Lowry. And so if you use a Bronsted-Lowry acid and base, what happens is the lone pair on the oxygen donates to the hydrogen, which allows this pair to go back to the fluoride. So this is why this is a base, because it's donating its pair of electrons to break the hydrogen bond and accept it. And that forms this coordinate covalent bond or dative covalent bond with this this hydrogen, and then leaving the fluoride with its full negative charge here. So it does make sense there. And again, we want to highlight this bond as a coordinate covalent bond. A bond where one species donates both electrons. Okay. Now, also in these terms, we will use two terms that are applicable in organic chemistry and I guess a little bit in transition metal chemistry as well, which is nucleophile and electrophile. And nucleophile means essentially positive seeking. And so the Lewis base is your nucleophile. It has an extra additional pair of electrons that are available to bond, and so it's looking for something to bond with. Whereas this, the Lewis acid, is the electrophile, okay? Because it's willing to accept a pair of electrons here. So the Lewis acid is the electrophile, the Lewis base is the nucleophile. And you could talk about this in terms of inorganic and organic chemistry. And like we said, these ideas apply to transition metal chemistry and organic. And so in inorganic, when we talk about complex ions, we see that because let's say we have a copper 2+ ion in the middle, and you have chloride ions forming a complex ion with this transition metal, okay? And so this is CuCl4 2-. But what you're happening here is the Cu2+ is your electrophile. So that would be called your Lewis acid. Whereas the Cl- with its available pair of electrons bonds and forms a coordinate covalent bond with it. And so then this is your nucleophile or your Lewis base. Okay. So that's how we apply that terminology in terms of inorganic species. Now with organic species, you have those nucleophilic substitution reactions, right? So your SN1, SN2, things like that have this same idea happening, where you have your OH- and then your organic compound. And what happens is that OH- donates to the carbon, which then allows this Cl to break off. Okay, so in this case, your OH is your nucleophile. And this is your electrophile. Okay, but we call it nucleophilic substitution because what you're doing is you're substituting a nucleophile, and that's why we call it nucleophilic substitution. There is electrophilic substitution, there's electrophilic addition, all that kind of stuff. But when we're focusing on this, this is nucleophilic substitution. That's where that term originates from. Questions about that? Okay. The next section is equilibrium law, which means how do our weak acids and weak bases behave in terms of equilibrium? Because remember, our weak acids and weak bases dissociate only partially, so there's an equilibrium occurring. That's why you write a double arrow when you write those reactions out. So when you have something like this, there is a double arrow because it goes back and forth in equilibrium with each other. Okay. Now, this equilibrium, because the species that's not water is donating a hydrogen, this is known as a acid dissociation reaction, which is signified by Ka. Dissociation reactions always involve water in the reactants. So if you see water in the products, that's not an acid dissociation reaction. That's probably a reverse of a dissociation reaction. Much like you can see here with NH3, you see that NH3 is accepting a hydrogen. So it's acting as a base. So this is a base dissociation constant, or Kb. Okay. So you have to be aware that if they ask you, here's a species and write the acid dissociation reaction, you would react it with water to form H3O plus and the conjugate base. Or if it's a base dissociation reaction, you react it with water to form the hydroxide ion and then the conjugate acid. So know that that is what dissociation means in these terms. Now, it turns out that a conjugate acid base pair this which has a Ka and a Kb. It turns out when you combine a conjugate acid base pair together, NH3 and H4, their reactions together, you end up getting just H2O yields, or I guess H plus OH minus, which is Kw. So therefore, when you have a conjugate acid base pair, Ka times Kb is equal to Kw. So you can solve for the acid dissociation or the base dissociation based on the Kw value at that temperature and knowing the Ka or Kb of the other one. But you have to remember that dissociation reactions have the water on the left. Okay, so make sure you remember that. That's how the reactions add up and cancel each other out. Questions about that? Okay. Now, again, much like H plus and OH minus, Ka and Kb's are generally very, very, very small. So the IB, what they'll do is they'll write it in terms of pKa or pKb, which again is just the negative log of what it's being attached to. So pKa is a negative log of Ka, and pKb is a negative log of Kb. So the thing you have to think about, though, is, again, much like H plus and pH, because it's a negative log, the size of the value reflects opposite. So a large Ka would mean a low pKa. Which means a stronger acid. So the lower the pKa is, the stronger the acid is, because the more it dissociates. And the IB in their data booklet writes everything in pKa. So you are expected to be able to undo that value and figure out what the Ka is based on, again, algebra by reversing the log here. So you do want to think about strengths in terms of pKa and Ka. So know how to compare pKa's and Ka's as well. And again, if I'm the IB, I mix it up, right? I give you a question where there's 4 acids and 2 of them are Ka's and 2 of them are pKa's, and then you have to compare the strengths. And so for students that don't think about that and think about converting, then they're going to mix it up and mix up which one's the one. Now, having said that, you could do that on multiple choice because they'll make the exponents different enough that it'll be obvious. And so, like, if they give you one where it's like 1 times 10 to the negative 4, pKa is 6.52, and then 3 times 10 to the negative 8, and then like 2.52, you can order these because usually the rule of thumb is if you look at the exponent, that gives you an idea of what the pKa will be. So 1 times 10 to the negative 4 is about 4, and 3 times 10 to the negative 8 is a little less than 8, like 7.7 or something like that. So you could do this without a calculator and just kind of estimate based on the exponent. And the IB should give the numbers significantly different so that you can easily do that with mental math. So don't worry too much about that, but just know that you could usually use, the negative exponent to give you an idea of or the exponent itself to give you an idea of the pKa or pKb respectively. Now, what you do have to remember is Rice charts, where you have a Ka here and you're having to do a Rice chart here, and that Ka is equal to H3O plus times F minus over HF. Okay, and so that's your Ka. And so you have to solve for what all of those variables are to be able to solve for Ka, or use Ka to solve for one of the unknown variables. And there's 2 methods that you might run into. Well, actually, to be honest with you, here you're not going to really have the perfect square rule because we're doing dissociation. So there's no square that you can square root. So it's always going to be the 5% rule. Okay. The 5% rule states that we assume the X is much, 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 much less than the original concentration of the acid. We'll write HA for generic acid here. So therefore it is negligible in the calculation. Now you still have to plug that value in at the end. Even if you're going to assume it, you still have to subtract it from the original concentration. But for your calculation part, you omit that minus X or that plus X when it's attached to a number. So just keep that in mind here. And then pay attention to what your reaction is doing, because in this problem, you get H3O plus so that you can directly solve for pH. But in bases, you get OH minus, and so then you're directly solving for POH, which is the opposite of what our pH is. And so you might evaluate that number incorrectly. So be wary about that and really pay attention to what species you're dealing with in the problem here. Questions about that? Okay. We're going to go on to the big kind of last subtopic here. I know I'm saying last with like an hour and 8 minutes left, but it is a significant, we may still finish a little early, but it is a significant chunk of different ideas that are incorporated here. And that is pH curves. Okay. pH curves incorporates a lot of different things. Now, pH curve itself is that graph due to the titration. And so let's see. I'm going to try to draw this pretty big because I'm going to try to write a lot of stuff on here. Okay. So here a pH curve has a y-axis of pH and an x-axis of volume of, in our case, base added. Because I'm going to do this acid titrated with a strong base first for our purposes here. Okay. Now, we'll call 7. Actually, I'm not going to draw 7 because I'm not sure how my curve is going to look. But first of all, I'm going to draw a strong acid with a strong base. So a strong acid will start here. And go like this. And I think we'll call that about 7. A weak acid with the same concentration will start higher but it will still end at the same volume. Because remember we said before, what matters for neutralization is the moles of acid, not whether they're strong or weak. And so what you'll see is its equivalence point will be slightly higher than that. But both values actually turned out a lot better than I thought it was going to. Require the same volume of base to neutralize if it's the same concentration and the same volume of weak acid or strong acid. Okay. And so these 2 points, actually, I'll call this and this are known as our equivalence point. Okay. And so that's where neutralization has completely occurred, where the amount of base and amount of acid you have completely neutralized each other, and all you're left with is a salt and water. That's all that's left at the equivalence point. Now, again, the pH at the beginning is based on how much it dissociates. So a weak acid will always have a higher pH than a strong acid with the same concentration. Now, notice, again, same volume of base to neutralize. We're assuming the same concentration, the same volume of acid, I should say, in this case. Now, other aspects of this graph that you need to be familiar with, and they are all related to the weak acid. Okay. When you get halfway to the equivalence point, okay, there is something that's unique happening there. And we'll talk about this a little bit later, but at this point, you've neutralized half of your acid. So therefore, the amount of H plus and the amount of A minus are the same. You've neutralized half the acid so that you've made half the amount of salt that you have for the neutralization. So they're the same. And when they're the same, pH is equal to pKa. So pH is equal to pKa at that given point. So if you read that point on the graph, you'll be able to predict or estimate what the pKa of that weak acid is. Now for weak bases, it's the same idea, but your pH is still your pKa. So you'll have to do POH is equal to your pKb. So if it's a weak base, you have to flip that around. Okay. And in this region right here, okay, that is known as our buffer region. And we'll talk about what that means in a little bit. Now, you also need to be aware that you want to choose an indicator whose endpoint is relatively close to the equivalence point. So the pH at which the indicator changes color should be about the same pH as the pH of the equivalence point of the neutralization. So these two reactions might require different indicators to get the best results, and that's okay. And you're given some of these indicators in your data booklet. So you don't have to memorize indicators per se. Phenolphthalein is kind of a common one that you should know, but all the other ones that are important are listed in your data booklet. Okay. Now, the other thing though is this. We can also assume for a strong acid, because it dissociates 100%, that we could also assume that your pH is, let's see, how do I say it? Actually, let me see. Okay, is equal to negative log of H plus, and H plus is equal to your acid concentration. So you could, if it's a theoretical titration curve, you could assume, since it dissociates 100%, that whatever your concentration of H plus is, that would also be the concentration of your acid, because we are assuming that it dissociates 100%. So theoretically, you could just take the original point on a graph that's given and figure out what the concentration of the solution is. Not most accurate in real life, because even strong acids don't dissociate 100% based on the concentration. So it's best to do the titration to get the equivalence point and figure it out that way. But technically, you could figure it out using this. And the weak acid will always be higher with the same concentration. Let me see this. Okay. same concentration, same volume. You have to have those qualifiers to make this true. Now, if you had a weak base, I'm going to sketch this on here, even though it says volume of base data at the bottom. If you had a weak base, it would start here. And let's see. It would start up here. I love it. Weak base and strong acid here. It would start up there in the basic range, and its equivalence point would be below 7. So you would see it down here for its equivalence point below 7. And then this point here, pH is equal to pKa, but then pOH is equal to pKb as well. So if you subtract your, I guess we're assuming at 25 degrees Celsius, you can subtract your 14 minus your pH to figure out your pOH, which then is your pKb for a weak base. So all those points are you're expected to know. That's funny bone. Okay. Questions about that? Now, let's talk about two ideas here. These are the last kind of two major ideas for this topic. The first one is
Mr. Chung,
yes, hold it.
could you go over what the buffer region is?
Yeah, that sorry. Actually, you know what? We'll do that here and then we'll talk about the salt here. Okay, so that's a good question. The buffer region. I was gonna wait to buffers to do that, but I think buffer region is a little bit different than buffers. So let's do the buffer region here. Okay. And so the buffer region, actually, maybe it is more buffers. So we'll do buffers first. The buffer region is an area of the pH curve where the solution resists pH change when a small amount of acid or base is added. Okay. And so the buffer region occurs when you have two weak species that can accept and donate hydrogens. And so when you have a weak acid with a strong base, you produce NaF and H2O. But really, because Na doesn't do anything in this reaction, what you're really producing is HF plus OH minus yields F minus plus H2O. And while you are titrating, you're going to increase the amount of these, or you're going to increase the amount of HF minus as you decrease the amount of HF as you're adding more and more base to it. But in that buffer region, you have an adequate amount of HF and F minus in the system. And when you have an adequate amount of that, what that means is that it's going to buffer or absorb any change in H plus or OH minus to stabilize the pH. And that's what a buffer does. And so when you add a base to it, you generate F minus, and therefore a buffer can occur because the HF absorbs any OH minus. And the F minus absorbs any additional H plus in there to form its conjugate. So a buffer can only occur if the conjugate acid base pair is present in there, because one of the acid in the conjugate acid base pair will absorb OH minus, and the conjugate base will absorb the H plus. And this only works if the H or the OH minus will actually stay bound to it. That's why strong acids don't work as buffers, because even if you have Cl minus, it will, even if it bonded with the H plus, it would just dissociate again because it's a strong acid. So you don't have to worry about that as much in this concept. Okay. So the buffer region is that presence of a conjugate acid base pair, really. And that conjugate acid base pair allows the absorption of H plus and OH minus, so the pH resists change. Did that explain it, Holden?
Yeah, thank you.
Okay, no, you're welcome. That is kind of a good transition, because in a titration, you generate a buffer organically because you're titrating and you're going to naturally make those species that form a buffer. But you can make buffers manually, like without doing a titration, but the same concept. And so to make a buffer, just like we said before, you need to have a conjugate acid base pair that is weak. Because weak means it doesn't dissociate, so it can actually absorb the H plus or the OH minus that's being contributed by an outside source. So conjugate acid base pair that is weak. And so you could do this as, an acid or a base with its salt. And so you can mix a salt in with an acid or a base with its conjugate and form that. So for example, we could mix HF with NaF, because NaF is going to dissolve. It's going to produce a significant amount of F minus to be able to absorb a addition of H plus or OH minus, because the F minus will absorb any H plus and the HF will absorb any OH minus. And the key word here is a significant amount of F minus, because yes, you could argue that HF alone would make some F minus, but the amount of F minus that it produces is so small that any amount of OH you would add in there would, any H plus you add in there would probably break that buffer, if that were considered a buffer. So you want a significant amount of both of the conjugate acid base pair, and that usually requires you to add a salt to inflate the number of the conjugate. That's the point of this, is to produce more conjugate base to make a better buffer. Questions about that? Now, like we said in titration, you can do that as well. You could actually add a strong acid or strong base to a weak acid or weak base mixture or solution and accomplish the same idea, because like we said before, if we add a strong acid to a weak base, we will get the conjugate, and we'll get it in an abundance enough such that it can become a buffer, because the base itself alone doesn't make enough conjugate acid to be considered a buffer. And so the presence of both of these two species here, because you added HCl, allows for the buffer to occur. But there is a stipulation for this type of buffer formation. Okay, what's the catch with this type of buffer formation? What do you have to be careful about when you're making this solution? Any ideas? What do you have to be careful about when you're mixing HCl with NH3 to make a buffer? What do you have to be careful about? Any ideas? Think about the reaction that's occurring, right? You have to be wary of how much HCl you add into it. Because if you add too much HCl, then you won't have any NH3 left to create the buffer. You'll have used up all the NH3 and all you'll have is NH4 plus. So the amount of the strong base or strong acid has to be less than your weak acid or weak base to make a buffer. Generally, the ideal buffer is half. You put half of it. That's why this titration curve has that kind of optimal pH equals PA at half. But sometimes you have to adjust the amounts to make the right pH for your buffer. So you might add more acid or more base to your solution to kind of vary that buffer pH depending on the situation. But make sure you have less strong base or strong acid than you do weak acid or weak base. Okay. And so I think the IB calls this the partial neutralization method. I haven't seen that term until I was kind of looking at this right now, but partial neutralization is one technique. And the other technique is just adding a salt with the conjugate in there. With the conjugate salt, it doesn't matter how much you put in there. As long as you put some in there, you can put way too much or too little. Like even as long as there's a significant amount in there that you're mixing in the solution, it doesn't matter. With the weak acid base and the partial neutralization, it does matter how much you put in there. Questions about that? If you want to look at some of the practice questions, go back to the topic 8 and 18 notes to look at some example questions. I'm not going to write those out right now. You can kind of revisit those on your own. The last concept for today is predicting pH of salts. Okay. Now, this is twofold. There is the general way to do it, to identify just by looking at a salt, and then the method in which you have to justify your answer. And so using reactions. So there's the basic way, no pun intended, where you look at a salt like, I don't know, something like NH4 NO3. Okay. And that's a salt. And you, again, identify what acid and what base originated from it. Well, NH4 originated from NH3. And NO3 minus originated from HNO3. Well, this is a weak base and a strong acid. So this is an acidic salt because the parent acid and base were different strengths, and the stronger, if there's a strong or stronger, I should say, species, then that dictates the salt. So in this case, a weak base plus a strong acid makes an acidic salt. NAF came from NaOH and HF. So this is a strong base, weak acid. So therefore, this is a basic salt. And this salt itself helps you predict the equivalence point, because an acidic salt should have an equivalence point less than 7. A basic salt should have an equivalence point above 7, which helps you decide what indicator is best appropriate for your titration. Okay. If it's a strong acid and strong acid, a strong base and strong acid, I should say, sorry, it will be neutral. The only thing that might be tricky is a weak acid with a weak base, because neither of them are strong, but one is usually stronger than the other. And so whichever K is larger. So you'll compare Ka versus the Kb. Don't compare Kas, compare the Ka versus Kb. Whichever one's larger, that's the pH of the salt. So if the Kb is larger, then it's a basic salt. If the Ka is larger, it's an acidic salt. If in the rare occasion that they're the same, then it's a neutral salt. But don't always assume all weak acid, weak base combinations are neutral. Okay. Questions about that? Now, I guess the advanced concept of this is to prove using equations. Wow, my handwriting is really failing me right now. Okay. And what that means is we're going to talk about what's called salt hydrolysis. So when a salt dissolves in water, it produces the parent species, acid and base. And some of those parent species will stay together and some of them will dissociate. And so that's how you prove whether a reaction is going to produce an acidic or basic salt or neutral. Because let's say you have something like NaF, which we talked about before. NaF, when it reacts with water, will form NaOH plus HF. Okay. But when you look at those products, NaOH is a strong base. And so what happens is the reaction really is Na plus F minus plus H2O yields Na plus OH minus plus HF, because the salt dissociates and the strong base dissociates. Now, the Na doesn't do anything. It's a spectator ion. So we remove that. And so the actual reason why it's basic is because the F minus, the weak conjugate base, reacts with water to form the weak acid with OH minus. And so it's actually, ironically, the weaker part of the species that actually determines the pH, even though the stronger part is what we kind of look at to identify it. The weaker part is what justifies the pH of the reaction. So if they ask you to explain why that salt is basic, you would focus on this equation here. Like providing an equation, you would say, well, the salt dissociates and this part of the reaction occurs. I guess you would actually write double arrow here now I think about it, because it is a weak equilibrium. Same idea with like NH4Cl. That reacts with water to make NH4OH and HCl. Okay. Now, really NH4OH, to be honest with you, is NH3 and water. So I guess you would write it that way. But again, HCl is a strong acid. So even though it's NH4 plus Cl minus plus H2O, yields NH3 plus H2O plus H plus Cl minus, the Cl minus is canceled. So it becomes NH4 plus H2O yields NH3 plus H2O plus H plus. And you could write this as H3O plus if you wanted to. But that's your justification for why the reactions end up forming a acidic or basic solution. Okay. questions about that? I guess just going back here really quickly, because I saw this idea. These set of equations here is what buffer action is. Buffer action is the set of two equations that explain why the buffer is able to absorb H plus and OH minus. So those are the buffer action equations for this. Okay, so make a note of that in this for your revision as well, in case they ask you for buffer action equations. Any final questions before I end the recording? All right, that was the end of topic 18 revision. So this whole video is topic 8 and 18. I will upload it onto YouTube hopefully later today so that you can have access to it and revise later on. Thanks for watching. Let me stop the recording.